Add 1/10 to itself 10 times, and the computer will tell you the answer is not 1. That tiny error has a precise cause, and it lives inside the way fractions get turned into binary. Integers were easy. Fractions are where it gets hard. By the end, you will see exactly why the number 0.1 is trouble. Start with what a fraction even means. In our everyday base 10, the number 0.abc means a over 10 plus b over 100 plus c over 1000 and so on. Each place is the next power of 10 in the denominator. Binary works the exact same way with one change. Each digit is now only 0 or 1, and the denominators are powers of 2 instead of powers of 10. So a base 2 fraction 0.abc means a over 2 plus b over 4 plus c over 8. Asking for the binary form of a decimal fraction is really asking one question. Can we build our number out of 1/2, 1/4, 1/8, and the rest of the negative powers of 2, each switched on or off? Here is the recipe. Take 3/8, which is 0.375 as our example. The trick is to ask one question. What is the smallest power of 2 I can multiply this decimal by so that I get a whole number out? It must be a power of 2, because we are heading to binary. For 3/8, multiplying by 8, which is 2 to the power 3, clears the denominator. 3/8 times 8 equals 3. Now we have a whole number, and we already know how to write a whole number in binary. 3 is 1 in base 2. But that 1 stands for 3, and we multiplied by 2 to the power 3 to get here. To undo that, we divide by 2 to the power 3. In binary, dividing by a power of 2 just shifts the point. Starting from 1 with the point right after it, move the point left 3 places, padding with a leading 0, and we get 0.011. Notice what the whole recipe leans on. It only works if we can find a power of 2 big enough that, multiplied by our decimal, lands on a whole number. For 3/8, that power was small and easy. But that power is not always small. Sometimes it is enormous, and sometimes there is no such power at all, no matter how high we go. That is exactly where the trouble begins. Now the code that runs this recipe. We start with a value x. The first loop hunts for that magical power of 2. It keeps increasing p, the power, while 2 to the power p times x mod 1 is not 0. That mod 1 is the clever part. It strips away everything before the point and keeps only the fractional part. So as long as there is still a fraction left over, the loop keeps going. The moment 2 to the power p times x mod 1 becomes 0, the result is a clean whole number, and we break out having found our power p. Then we compute num as x times 2 to the power p. The next block is the integer to binary procedure you already know, building up num's binary digits by prepending. Finally, we shift the point back p places, padding the front with leading zeros where the binary string is short, place the point and print the answer. Let us step through it with x equal to 0.625. P starts at 0 and the loop climbs 1 power at a time, watching for the fractional part to vanish. If we print 2 to the power p times x mod 1 at each step, we see the leftover fraction shrink but stay non-zero. At p equals 0, it is 0.625. At p equals 1, it is 0.25. At p equals 2, it is 0.5. Then at p equals 3, 2 to the power 3 times 0.625 equals 5, a whole number. So mod 1 is 0 and we break. Num is 5. Now convert 5 to binary with the same prepend trick. 5 mod 2 is 1. 5 integer divide 2 is 2. 2 mod 2 is 0. 2 integer divide 2 is 1. 1 mod 2 is 1, and we stop. Reading the digits gives 101, so 5 is 101. Finally, we shift the point back 3 places, giving 0.101. The binary form of 0.625 is 0.101. Run the same program on a few values, and the easy ones fall out fast. 0.5 gives 0.1. 0.625 gives 0.101. Now run it on 0.1. Suddenly the loop has to climb through a long sequence of powers before the fraction finally clears, somewhere around 50 of them. We know it took that many because the answer comes back roughly 50 zeros and 1s long. In other words, 0.1 had to be multiplied by something close to 2 to the power 50 before it became a whole number. Think about what that means. A number that is a clean combination of powers of 2, like 1 times 2 to the power minus 3, which is just 0.001, is instant. But 0.1, whose mix of powers of 2 is not obvious at all, needed a program to find it. And the result ran about 50 digits long. And some numbers are worse still. Their binary fractions never terminate. They are in effect infinite. So here is the whole picture. Everything in a computer's memory is stored as bits, just zeros and ones. Integers are clean and quick to write in base 2. Fractions are a different story. A fraction that happens to be a tidy sum of powers of 2 converts instantly. But a fraction like 0.1 does not, and its honest binary form runs around 50 digits, while others run forever. Hardware only has room for so many bits, so a number like 0.1 cannot be stored exactly. It gets rounded to fit. That rounded, almost right value is why adding 0.1 to itself 10 times drifts away from 1. The error was never a bug. It is the unavoidable cost of squeezing an endless binary fraction into a finite box. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.